When it's time to move to another planet, Mars is right next door. But it's a freeze-dried rock, too cold for life. We could warm it up, but not like this.
Well, we know how to warm up planets. We're demonstrating that we know how to do that right here on Earth, where it's probably not a good idea.
We'll do it the old-fashioned way, with factories and global warming, on purpose. In 100 years, Mars will be warm, wet, and ready for life. It's called terraforming, and it sounds like science fiction. But it may be coming to a planet near you sooner than you think.
That's not something for 500 years in the future. That's us. We're going to Mars.
What would it take to make water flow on a world where the average temperature is 80 below zero? Or turn bare rock and dust into soil where forests could grow? What would it take to terraform Mars? Create a planet more like Earth, where humans could breathe the air? It would cost billions and take hundreds, if not thousands of years to accomplish. But transforming Mars from a barren rock into a living world is not as far-fetched as it may seem. And our long-term survival could depend on it.
If you're a threatened species, which, let's face it, we are, you don't want to all be in one small habitat. You want to be diversified.
Terraforming is already on its way from science fiction to science fact. Here on an 18,500-foot volcano in Mexico called Orizaba. It's a magnet for climbers, adrenaline junkies, and planetary scientists. Chris McKay is one of them, an astrobiologist interested in the possibility of life on other planets. His research takes him to extreme environments all over the world. Places that expose the limits of life on Earth. What draws him to Orizaba are the trees, and in particular, the tree line. At 13,000 feet, it's among the highest in the world, which means these pine trees live right at the edge of what trees can tolerate.
We're trying to understand what is it that sets the tree line. We want to know, why do the trees grow down there, but not here? Clearly it's warmer down there and temperature is the key variable, but something in the forest ecosystem is responding to temperature.
McKay and colleagues from the National University of Mexico have been experimenting with seedlings above the tree line, following their progress over time.
So that's 152 for?
Yeah, 152.
It's basic environmental research to understand how the ecosystem works. But for McKay, there's another motive, with implications far beyond this mountain and even this planet. He hopes that discovering the minimum requirements for trees on Earth will get him closer to understanding what it would take to grow trees on Mars. At the moment, Mars looks like a bad place to grow anything. 50 million miles farther from the sun than Earth, it's a frozen desert of rock, ice, and dust. And it's been that way for billions of years. It's little more than half the size of Earth, but it has the same land area as all the continents on Earth combined. Intense ultraviolet and cosmic radiation sterilize the surface. Temperatures can range from 200 below zero at the poles to 80 above near the equator. But the carbon dioxide atmosphere is so thin, when ice thaws, it turns straight into vapor, not liquid. leaving the surface bone dry. To bring this hostile world to life would take planetary engineering on an almost inconceivable scale. But McKay believes the potential is there, waiting to be tapped. And the Orizaba volcano is a kind of living laboratory for understanding how it might happen.
Conditions on Mars are like the top of a very high mountain. Imagine a mountain on Earth 100,000 feet high. That's what it would be like on Mars. Very low pressure, very low temperature, high radiation, conditions so harsh that no life form on Earth could survive.
There are no 100,000-foot peaks on Earth, but the 18,500-foot summit of Orizaba is a polar desert like Mars, with a very thin atmosphere and temperatures close to zero. But at lower elevations, the temperature rises as the atmosphere thickens. Bare rock gives way to grassy tundra, and the first signs of life on the surface. Then, abruptly, the tundra gives way to trees, a dramatically more diverse ecosystem. This transition from a barren summit to an alpine forest is the same sequence of change that Mars would go through in the process of terraforming.
So the tree line is the key. We want to understand that transition. We want to know how much do you have to push Mars? How warm do you have to make it before the first forests, before the first trees can grow on Mars?
Terraforming has been a special passion of McKay's throughout a long career as a researcher and scientist on planetary missions. It began with the realization that Mars was not always as hostile to life as it is today. Orbiters have found dried up lake beds, river channels, and deltas all over the planet. Clues to an early Mars that was a warmer, wetter place than it is today. The rover's spirit and opportunity have found rocks and minerals that could only have formed in the presence of water. That means Mars must once have had an atmosphere dense enough to trap the heat of the sun like a greenhouse and create enough atmospheric pressure to keep liquid water stable at the surface. Conditions that could have been suitable for life. This was more than 3.5 billion years ago, when the solar system was young. Mars was still hot inside, and volcanoes pumped carbon dioxide into the atmosphere. Comets and asteroids pummeled the surface, heating and thickening the atmosphere even more. Closer to the sun, Venus and Earth started out the same way, but only Earth remains habitable today. As the Earth cooled, rain washed much of the carbon dioxide out of the atmosphere, dissolving it in the oceans, where it combined with other elements to form carbonate rocks on the sea floor. Today, most of Earth's carbon is locked up in these rocks. Very slowly, they're pulled back into the hot interior as the seafloor slides under continental plates. At the boundary, they sometimes melt and erupt through volcanoes at the surface, releasing a slow but steady stream of CO2 back into the atmosphere, producing enough greenhouse effect to keep the planet warm, but not too warm. As life evolved, it continued to transform the atmosphere for its own benefit, adding a mix of oxygen and nitrogen suitable for life. This delicate balancing act of biology and geology sustains our biosphere today. Venus wasn't so lucky. Closer to the sun, it turned into a runaway greenhouse. Its early oceans boiled away, leaving a world so hot and dry, visiting spacecraft have lasted only a few minutes on the surface.
Venus today is like an Earth that's been baked dry. It's very much like the Earth in many respects, but it's got 100,000 times less water. It's very, very hot. It's 900 degrees and very high pressure, almost pure CO2 atmosphere. So it's like your worst nightmare of the greenhouse effect.
Mars went to the other extreme. Not a runaway greenhouse, but a runaway icehouse. Only 1/10 the mass of Earth, it cooled off quickly. The volcanoes died out, and its once thick atmosphere gradually disappeared. With almost no greenhouse gas to trap the heat of the sun, create pressure and block radiation, Mars turned into the sterile, freeze-dried world it is today.
Mars is almost 10 times smaller than the Earth, and as a result, it has no plate tectonics to recycle sediments, it has no magnetic field to protect it from the solar wind, and it has less gravity to hold its atmosphere. All of those factors cause Mars to lose its atmosphere, become cold, and freeze up.
But remnants of the early atmosphere may still be there, buried, frozen, or bound up in the soil. And figuring out how to get them back is McKay's goal.
Think of it as a thought experiment. There's a world out there, we have evidence that it once had water, once had habitable conditions, it may have had life. Could we imagine bringing it back to life? Is that within the scope of our understanding of planetary science and the technologies that we humans can deploy?
To terraform Mars, we'll need to rebuild its early greenhouse atmosphere, and that will require carbon dioxide and water. There's some carbon dioxide frozen at the poles as dry ice, and more saturating the ground, like water in a sponge. The gas releases in the summer months, thickening the atmosphere by 30%, and then condenses back to the ground when it turns cold again. That accounts for some of the original CO2 atmosphere, but there should be more. Scientists have long suspected that much of the early CO2 reacted with elements in the ground to form carbonate minerals. The rovers Spirit and Opportunity have instruments specifically designed to see carbonates, but so far, they haven't found them.
We don't know what happened to the initial carbon dioxide atmosphere of Mars. It is possible that it's gone forever, and that would be bad news for the notion of making Mars habitable. It's also possible that it's hidden in places that we don't see. After all, we've only dug down below the surface a few inches. It would be premature to think that we know everything that's going on about Mars. But it's a mystery, and it's certainly one of the key questions that needs to be answered in terms of, can Mars be restored to habitability? Is there enough carbon dioxide available to make a thick atmosphere? If the answer is yes, then we've got a plan. If the answer is no, then that's a serious problem, and it pushes off restoring Mars to habitability to some future technology that we don't understand yet.
Still, McKay is optimistic about the carbon dioxide, and he's even more confident that there's plenty of water on Mars in the form of ice. In 2002, an orbiter detected vast reservoirs of hydrogen, shown in blue here. It's the H in frozen H2O. In 2008, the Phoenix lander touched it for the first time. Water ice, just inches beneath the surface. And recently, the Mars Reconnaissance Orbiter found even more. A glacier under a layer of dust closer to the equator. It may be one of many on Mars.
When we look at Mars today, we see all the elements needed for life, and everything we've learned about Mars suggests that recreating the habitable conditions it once had may be possible.
Vital elements of the early atmosphere may still be on the planet, but immobilized by the extreme cold. To terraform Mars, we'll have to bring them back to life again after 3.5 billion years in the deep freeze. Mars is a dry, frozen world today. But colonists from Earth will someday be looking for ways to make it more like home.
The first and most important step in making Mars habitable is to warm it up. The fundamental problem with Mars today is it's too cold.
We'll have to warm Mars from its average of 80 below zero to about 25 below to get terraforming started in the warmest regions near the equator. And it would take something pretty dramatic to generate that kind of heat. One person who has pondered the problem is Robert Zubrin, an aerospace engineer, author, and ardent proponent of colonizing and terraforming Mars.
Initially, I thought about anything would be ready for its first test. Some of which involved significant violence.
He considered hydrogen bombs to melt ice and heat up the atmosphere, or corralling space rocks from the asteroid belt and crashing them into Mars. But he's had second thoughts about that.
I've come to realize that while some of them might be workable in principle, that none of them are really workable in practice.
Zubrin's long-range vision of Mars involves people, permanent colonists calling the planet home. And they'd want to survive the process of warming it up.
The people who are actually going to terraform Mars are going to be the people who live on Mars. Okay, they are the only ones who will have a significant enough stake in the outcome of terraforming Mars to want to expend the resources that would be required to change a planet. So they're not going to want to do things like exploding hydrogen bombs on the South Pole.
In fact, there is an easier way, and we've been practicing it on Earth for the past 150 years.
We know how to warm up planets. We're demonstrating that we know how to do that right here on Earth, where it's probably not a good idea.
By burning fossil fuels, the carbon remains of ancient plants, we're pumping out carbon dioxide faster than the Earth can take it back in. In the process, we're increasing the ability of our atmosphere to trap heat from the sun. And we're seeing the kinds of results that terraformers would like to see on Mars.
Warming up planets is something we know how to do. We would do exactly on Mars what we're doing on Earth. We're going to have to set up literally little factories on Mars whose intent is to produce greenhouse gases.
It would be prohibitively expensive to bring fossil fuel from Earth, and even if it weren't, it would take thousands of years to produce enough CO2 to make a difference. But there are more potent greenhouse gases that could be made from materials already on the planet. At Caltech, Margarita Marinova has been studying them, exposing them to infrared light to see how efficiently they capture heat.
Some of them just let that energy pass straight through them, but some of these gases actually absorb the energy.
The most potent, containing sulfur and fluorine, have a super greenhouse effect, thousands of times greater than carbon dioxide.
So they really put a lot of punch in for a very small amount of the gas.
Fluorine and sulfur are both contained in the Mars soil. So you might imagine these factories pulling in Mars air, scooping up Mars dirt, going through a chemical process, producing these super greenhouse gases, and releasing them into the atmosphere. In a sense, the hardest part of this whole story of warming Mars and introducing life is that first step. That first step of producing the super greenhouse gases on a planet with no infrastructure, no facilities, nothing. Everything's got to be built from scratch.
McKay estimates that it would take about 100 years to warm Mars to the point where liquid water could exist on the surface. That means pushing average summer temperatures above 32 degrees in some areas, and generating enough gas to create at least 10 times more atmospheric pressure. The factories could never accomplish that on their own. But they won't have to. Just slightly warmer temperatures would cause what's left of Mars' ancient CO2 atmosphere to start gassing out of the ground in the polar ice caps and stay in the atmosphere year-round. Water ice would start to thaw, adding vapor to the atmosphere. And water vapor is another potent greenhouse gas.
As the atmosphere gets thicker, it gets warmer. And as it gets warmer, the atmosphere gets thicker, and the process just grows automatically.
We'll need to warm Mars roughly 10 times more than we've warmed Earth with carbon dioxide over the past 100 years. But we'll be doing it with the help of super greenhouse gases, which are thousands of times more efficient than CO2.
On Earth, we're not trying to warm up the planet. It's happening despite our best efforts to prevent it. Imagine if we actually tried to produce greenhouse gases, we maximize their efficiency for warming a planet and release them on purpose. It's not hard to imagine that we could do 10 times more warming than we're doing now.
When the atmosphere thickens to the point where ice can thaw and remain stable as liquid, the pace of warming could accelerate even more. Phoenix found that a few % of the surface soil is a carbonate mineral like chalk. Satellite instruments have picked up signals that these carbonates may be widespread over the planet. At the same time, the rovers have both found minerals that formed in extremely acidic water, virtually sulfuric acid. Today, the ground is dry, but it may still be acidic, and combined with carbonates, that could be a recipe for making carbon dioxide gas. To demonstrate, McKay mixes carbonate, ground up chalk, with simulated Martian soil containing dry acid, and then adds water.
So when I add the water, what I expect is that the water will activate the acid will decompose the carbonate, and CO2 will release. And you can see it's happening. You see the gas is being released, it's foaming. I'm pleased to see it. It's not a real surprise. I expected it to happen, but still, when you actually try something and it works, that's always a good thing. CO2 is being released. Gas is coming out of the soil. The components are there. The acid and the carbonate are there, but without water, they don't react. This could be the way we make a thick atmosphere on Mars. Just add water.
McKay calculates that after 100 years of warming, most of the available carbon dioxide is out of the ground, thickening the atmosphere and turning the Martian sky blue as it scatters the sunlight. Ice thaws and water pools in ancient depressions for the first time in billions of years. As water evaporates, vapor builds up in the atmosphere, and it begins to rain. In the colder regions and higher elevations, it snows.
We can imagine that after 100 years of warming, Mars has now got a thicker atmosphere, it's got water on the surface, it's got clouds, it's got rain again. From space, it would look a lot like Earth. It would look like a blue marble. We would have, once again in our solar system, 2 blue marbles. I think that would be an amazing sight.
Much of this new blue Mars would be an icy world, like summer above the Arctic Circle, with atmospheric pressure equivalent to a mountain twice the height of Mount Everest. But it would be habitable in a way that Mars today is not.
The surface conditions could be fairly pleasant. The real problem is that it's not breathable. It's a carbon dioxide atmosphere, and humans can't breathe pure carbon dioxide. There'll be very low levels of oxygen in with the carbon dioxide, but not enough to breathe. So moving around on Mars after it's been warmed, you won't need a bulky spacesuit, but you'll need some sort of breathing system like scuba.
The first phase of terraforming is complete. But the next step, turning Mars green and producing a breathable atmosphere, will be a much longer and more difficult process. After 100 years of warming, Mars is ready for life. But what could survive here? Martian soil is something called regolith, pulverized rocks and minerals that may or may not include all of the chemical nutrients required by plants. The Phoenix lander looked for nitrogen, the most essential nutrient, and didn't find it. But the signal may have been blocked by other chemical compounds in the sample.
Unfortunately, we don't have any measurements that directly support or rule that out. But nitrogen is key. You've got to have nitrogen. It's got to be part of the ecosystem.
Nitrogen was almost certainly part of the original mix of elements on Mars. And the explosive energy of impacts may have converted it to mineral compounds in the ground. If so, the soil could be seeded with microbes like cyanobacteria that can start breaking down those compounds and get the nitrogen back in circulation. In the process, they'll photosynthesize, turning carbon dioxide into food and returning oxygen to the atmosphere, paving the way for more complex life.
So on Mars, if we want to have trees, if we want to have plants, if we want to have any life at all, we've not only got to get it warm enough, but we've got to make sure that the microbes are there doing their microbe thing, making their microbe nutrients that the trees need to grow.
Even after 100 years of warming, some parts of Mars would still be like the summit of Orizaba, a polar desert too cold and dry for any kind of plant life. Higher elevations and latitudes on Mars might never get past this stage. But lower elevations, closer to the equator, would be warmer and wetter, more like the lower slopes of the mountain. And on the way down, we can follow a virtual timeline of the planting schedule on Mars as the planet warms up. The first plants appear at about 17,000 feet.
They grow on the surface of this volcanic rock, and they're part of the first step that turns this hard rock into soil. The organisms are sliding their way under the rock, and they're living inside there because it's a slightly warmer, wetter environment. To those organisms, this rock is like a little greenhouse. But by living inside it, they destroy their very house. They release acids, which cause the rock to fall apart and flake off. Bits of rock fall to the ground. You can see them growing down here in the lower part of the rock, where they're also contributing to the flakiness of the rock. You can see the algae that were growing inside the rock. Life is playing a role in creating environments suitable for life. And this weathering is the first step in that transformation.
Around the same elevation, there's moss.
In a sense, that is what's happening, though. These moss and the lichens, they're attacking this volcanic rock. They're turning this mountain into dirt. It's a really hardy little organism. It can survive the high radiation, the low temperatures, make use of very little water. But most importantly, what it does is it photosynthesizes. It takes sunlight and makes plant material. It makes organic material. That material then goes into the soil and fertilizes the soil. These guys can take a mountainside and turn it into a garden.
They'll be the first imports of plant life from Earth, perhaps 50 to 100 years after warming begins. Lichens and moss thrive on carbon dioxide and get what nutrients they need from partnerships with microbes and photosynthesis. They build soil, help create more nutrients, and set the stage for what comes next. At about 15,000 feet on Orizaba, we find grass. The ecosystem is called tundra on Earth, a mix of grass and woody shrubs along with lichens and moss. As the plants grow and die, they enrich the soil and hold more moisture in the ground. Then, at 13,000 feet, where it's a few degrees warmer and there's a little more oxygen, tundra gives way to the tree line. A crucial milestone in turning Mars into a truly habitable world.
So the tree line is the key. That's what we need on Mars. Because trees and forests are really going to move Mars from just a warm carbon dioxide-rich planet to a planet with oxygen that's breathable by animals. Forests will be the engines that create the oxygen. And that engine of biological productivity is what will drive Mars into a state that will be a rich and diverse biosphere.
Research at Orizaba finds that 41 degrees is the minimum average temperature for the world's hardiest pine trees. When parts of Mars reach that threshold, the planet will be ready for trees of its own. It will begin with high-altitude pine trees imported from Earth. They can handle low oxygen and high radiation and spread their seeds on the wind without help from animal pollinators.
And so we go from bare, volcanic rock to a forest full of life. In fact, the tree line on Mars will look like the tree line here on the highest mountain in Mexico. These extreme high-altitude trees are the first organisms that might be producing significant oxygen on Mars.
It will take generations of work and possibly genetic engineering to get things started. But then the Martian forests will spread on their own, improving the soil and the atmosphere, creating a livable world for more than just plants. In the not-too-distant future, humans may have the tools to transform Mars from a cold red desert into a habitable world. But importing life and turning Mars green will raise questions that we've never faced before.
We can restore habitable conditions to Mars. The fact that we can, to me, opens up the question, should we? What we do will, I think, set the pattern that will reflect on us as a species for the rest of time. Mars will be where we set the precedent. And that's why I think it's very important that we do it carefully.
There's no sign of life on Mars today, and every reason to believe that it can't exist on the surface. The lack of water and shelter from radiation guarantee that. But there could be ancient microbes frozen in the ground, needing only warmer temperatures to wake up. If so, they could answer the biggest question in space science. Has life originated more than once in the universe? Mars and Earth have been swapping rocks for billions of years. What's knocked off one planet by an asteroid strike often lands on the other. And it's not inconceivable that microbes have sometimes gone along for the ride. So life on Earth may have come from Mars, or vice versa, which would be interesting, but tell us nothing about whether life originated anywhere else. But if Martian life turned out to be unrelated, a separate origin just one planet away in our own solar system, that would suggest that life crops up wherever the conditions are right. And a universe with billions of galaxies and trillions of stars could be teeming with life. It might also mean that life from Earth could be a threat to Martian life. So how should terraformers treat the natives, if there are any?
It would be best to try to answer that before we started warming up Mars, because what we do depends on the answer to that question. If we find that Mars has life that's the same as Earth's, then it doesn't matter, and we move down the path of sharing life from Earth with Mars. But if we find that Mars does have life, and that life is a separate, independent origin of life, then we do things completely differently, in my view.
In that case, McKay thinks we should sterilize all of our old space junk left over from previous missions. Even hundreds of years later, it could still be contaminated with bacteria from Earth. And then we should leave Mars to the Martians.
I would say our responsibility is to encourage that life to flourish and thrive. Diversity in life across planets is a good thing. And we would learn an enormous amount about how another biosphere based on that life might work. And that knowledge could revolutionize our understanding of fields like medicine and agriculture, as well as helping us understand the Earth by having a comparison biosphere.
But not everyone would go along with that approach, especially after going to the trouble of making Mars habitable.
I don't agree that that is a rational ethical position. The ethics need to be based on what is good for people, not what is good for bacteria. This idea of depriving humanity of a fully living world, not just for humans, but for a wonderful ecosystem of plants and animals and birds and fishes and all of this, in order to preserve this place for bacteria, is lunacy.
The alternative, though, is to play the role of the ruthless invader from another planet.
You think of the War of the Worlds kind of scenarios and all these creepy science fiction stories about aliens coming and saying, well, we want your planet, we're going to kill you.
We're friends! That's right! We welcome you!
You know, we think of that as evil. I mean, that's just not being a good neighbor. But I'm fairly convinced that we won't have this problem because I don't think there is life on Mars.
But even then, there's the question of whether we should tamper with Mars at all, whether it's dead or alive.
Picture the tracks left by the Mars rovers. It strikes me there's two different ways you can view that. One is the despoiling of a pristine, perfect natural landscape that should have been left alone. It's akin to tracks left by some four-wheelers who were driving on some beach and ripping up the dune grass, and it's vandalism. That's one way to look at it. The other is picture this evolutionary moment of life coming to a place with no life. To me, that's inherently good. In my view, if Mars is lifeless, it really changes the equation.
There are a lot of unknowns, and we need to understand Mars better to be more confident that something won't go crazily wrong that we're not expecting. But it's hard to have a bad consequence on a rock. You know, the rock will be a rock, and dormant life will stay dormant unless you do something about it and make it a more habitable place.
The world we see on Mars today is interesting, it's beautiful, it contains a fascinating scientific record, but in my mind, that must yield to the superior value of biology and life. Not just human biology and human life, but life as a phenomenon, that is the overriding principle, biology.
Because we live on a planet that's so full of life, we tend to think of disturbing nature as synonymous with disturbing life. And we don't have much experience with places that are truly, truly dead. In my view, Mars is like the vacant lot next door. Why not go there and, if it really is the vacant lot, why not plant a garden?
Once planted, the garden will take on a life of its own. And what happens then could shape the future of our species. Hundreds of years into terraforming Mars, pine trees are taking in carbon dioxide and exhaling oxygen, slowly turning the atmosphere into one that may someday be breathable by humans. And as conditions improve, so will the potential for a more diverse biosphere.
Earth's gift is the diversity and richness of its biology, and we can share that gift with Mars. And so it doesn't have to reinvent all this biology. It doesn't have to reinvent flowering plants. It doesn't have to reinvent mammals. It doesn't have to go through the dinosaur phase and get whopped by an asteroid and wipe them all out. They can do quickly what's taken us a long time to do. When we are bragging to the other planets and the other stars, what do we get to boast about? We Earth, well, we've got life. And if you're nice, we'll share it with you.
The lesson so far from the Orizaba tree line is that nothing exists on its own in a complex ecosystem. Trees grow where it's warm enough and wet enough for microbes to produce nutrients in the soil. And microbes thrive where trees and other plants cycle organic material back into the ground.
One of the lessons we get from studying ecosystems on Earth is that an ecosystem is not just a single plant or a single type of plant. It's a whole community of organisms, microbes, plants, all sorts of life forms growing together in a system.
For McKay, investigating the links between a living biosphere in Mexico and a potential biosphere on Mars opens a window on the nature and the future of life.
These are questions that I think are very deep and very important, and to me they connect to this mundane detail of making this measurement and that measurement in a glorious sort of way. Planetary science gives one an opportunity to think in terms of millions of years or hundreds of millions of years, and to think about what's going to happen to the Earth, what's going to happen to Mars. The question of the future.
McKay calculates that it could take 100,000 years for trees to transform an icy blue Mars with a carbon dioxide atmosphere into a warm green planet with enough oxygen for humans to breathe. But that's with present-day technology. Future terraformers may find a faster way.
We are in the position of a 20th century mind trying to solve a 22nd century problem. 200 years from now, they'll say, wow, these guys, they lived in the second half of the 20th century and they're talking about terraforming Mars. How prescient. But doing it with fluorocarbon gases and green plants, how 20th century can you get? They will accomplish this with 22nd century technology.
We can't predict exactly what a fully terraformed Mars would look like, how warm, wet, and diverse it might become. Water will fill low-lying basins, probably frozen at higher latitudes in the winter and open in the summer. High elevation terrain may be cold desert and dry grassland, and the highest, like the summit of the 85,000-foot Olympus Mons volcano, will be a reminder of what Mars was like before terraforming. But what happens to a Martian biosphere over thousands of years can be no more than a guess.
Where does Mars go at the end? It's a question I think about a lot. I think it's clear that Mars will go to this. It'll go to forests and trees. But where will those trees then take the planet? We won't have any control over that. Mars will follow its own evolutionary trajectory. If it follows the trajectory that Earth followed, then the oxygen will build up and it'll become a planet suitable for life like us. But maybe Mars isn't going to go quite that way, and it's going to end up moving in a path that we can't predict. It's not a problem if Mars has a mind of its own. It's a good thing. And for us as humans, it's a good thing because we will learn more about planets than by having just another exact copy of the Earth.
It may be 50 or 100 years from now, but eventually humans will be living on Mars. And it's not too soon to consider the choices we'll face when we get there.
That's fascinating to me, the notion that we as a species can ask that question, what are we going to do when we get to Mars? I want to see that dialogue happen. I want to see us as a species discussing it, because we're on the verge of getting to Mars. We can see that. That's not something for 500 years in the future, some distant new technology. That's us. We're going to Mars.
It's the nature of humans to explore, to investigate everything within reach. It's the nature of life to fill every available niche. And Mars will someday be available.
Just as birds transport the seeds of life to barren islands and turn them into lush places instead of just barren rocks with a few bacteria on them, we're the kind of bird, as it were, that can take the seeds of life from Earth and transport it to the barren islands that exist in space right now and turn them into bountiful, living worlds. So I think we will do that someday. We'd be less than human if we didn't.
Along the way, we may learn something about how living planets work and how to keep them alive.
The primary benefit the citizens of Earth will derive will be knowledge. And it'll be knowledge that may also have practical benefits in managing our own planet. No matter what we do in space, we are going to have to manage the Earth. And Mars is not an excuse to mismanage the Earth. In fact, we have to view it the opposite. Mars is part of the lesson plan in learning how to manage the Earth.
Mars lost its early atmosphere in part because it was small and lacked the internal heat necessary to keep it going. A terraformed Mars would eventually suffer the same fate, but it would happen very slowly, over tens of millions of years.
Eventually, Mars will lose its atmosphere. It won't be habitable forever. But then nothing is forever. Even the Earth won't be habitable forever.
In the far distant future, as our aging sun grows larger and hotter, the inner planets, Mercury, Venus, Earth, and Mars, will be burned to a crisp. If anyone still lives in our solar system by then, they will have long since moved on to better neighborhoods. Perhaps one of the moons of Saturn, like Titan, or farther on to another star system. If so, Mars may be the place where their distant ancestors first learned how to live on another planet.